In the last video we saw that the steady-state response of a linear stable system with transfer function g of s to a sinusoid of certain frequency and amplitude is another sinusoid with the same frequency but different amplitude and crossings of zero at different points. We call the ratio between the amplitude of the output and the amplitude of the input the gain of the system at that frequency, and the distance between the crossings expressed in radians the phase shift. We also saw that both the gain and the phase shift are defined by a very particular complex number, a number that comes from the replacement of s by j omega in g of s. Writing the complex number g of j omega in its polar form, that is, the magnitude g times the exponential of j phi, we find that g is equal to b over a, and that phi is equal to omega L. Finally, we saw that having the gain and the phase shift of the response to sinusoids of all the possible frequencies is a way of completely characterizing the dynamic response of the system, because with that information it is possible to build both the transient and the steady-state response of the system to any bounded input. So as a consequence, we are interested in the complex number associated to each frequency. In general, these are different complex numbers. So how do we store all that information? Well, one possible way could be to build a table. For its frequency, omega, we calculate the frequency response, or in other words, the associated complex number. And from that, its module, the module of g of j omega, and the angle of such complex number. So, for example, imagine that we are analyzing the response to a sinusoid of 1 radian per second. We just have to take g of js and replace s by 1 omega. Now imagine that what we get is the complex number 1 minus 1j. Well, in that case, the magnitude would be, let's see, the square root of the real part squared plus minus 1 squared, that's the square root of 2. So the amplitude of the output sinusoid is going to be the square root of 2 times bigger than the amplitude of the input sinusoid. Similarly, there's going to be certain phase shift, which is given by the arctangent of the real part, the imaginary part, that's minus 1 over 1. And I think this is minus pi over 4, or if you prefer, minus 45 degrees. And in this way we could continue calculating the frequency responses to other frequencies. For omega 2, g of j omega 2, for omega 3, g of j omega 3, and from that the gains and the phase shifts. Incidentally, remember that this table works both ways. If we have the transfer function g of s, we can calculate the gain and the phase shift at each frequency. But if g of s is unknown for us, as long as the system is stable, we can expose the system to a sinusoidal input and wait until the steady-state regime is reached. Then we can extract the change in the amplitudes of the sinusoids and the phase shift, the distance between the crossings, and from that phi, and this is equal to g. And with those two, obviously we already have the complex number, the frequency response. Okay, in any case, as you can realize, working with tables is not very practical because they can only convey the information relative to a limited number of frequencies. It is certainly more convenient to resort to a graphical representation of the frequency response. And the reason is that in a graph we can always perceive tendencies, and in that way guess what the response at certain frequency will be like, even if it hasn't been explicitly calculated. And probably the most straightforward option in that sense is to gather all that information in a single graph. That is, to take all these complex numbers and draw them in the complex plane. In order to differentiate each response from the others, we have to label each point with the corresponding frequency. Omega 3, omega 4, and so on. Now, filling the gaps, joining the points, we have the so-called polar plot or Nyquist plot, named after Harry Nyquist. As we shall see, the Nyquist plot is used to assess the stability of closed-loop systems. However, it's not usually employed to design control systems because it has some drawbacks. Firstly, it is very difficult to locate frequencies in the plot. The distance between 2 points is not representative of the distance between the associated frequencies in the spectrum. So it's difficult to guess where a certain frequency has its response based on known responses of other frequencies. Let me give you an example. If I'm told that this point here is g of j1, and that this point here is g of j10, I don't really know where along this curve g of j5 is. I have no clue for that, and that's a problem. Secondly, the multiplication of complex numbers is not a straightforward operation. So when a transfer function is the result of a multiplication, like for example g of s equal to g1 of s times g2 of s, having the polar plots of each one of the factors is no help for finding the polar plot of the overall g of s. And for those reasons, Hendrik W. Body came up with the idea of a different graph, a graph that shows explicitly all the frequencies, and in which the curves of the factors, the curves of G1 and G2, can be added up to yield the frequency response of G of S. And the idea is to use not just one plot, but two of them. One for the gain of the system at each frequency, and the other for the phase shift. That way, the horizontal axis is reserved for the frequencies. Now, if you're familiar with things like waves and electromagnetism, you probably know that the spectrum of frequencies is usually represented in a logarithmic scale instead of a linear scale. Think that there are potentially infinite frequencies to consider, so using a logarithmic scale is a good way to take into account a great number of them. So for example, this point here would be 0.1 radians per second. This point would be 0.2 radians per second, and this point would be 0.3, and this one 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and this one would be 1 radians per second. And now this point here is not 1.1 radians per second, but 2 radians per second, and this would be 3, 4, 5, 6, 7, 8, 9, and 10. And now we continue with 20 and 30 and so on and so on. And going down is the same. Here we would have 0.09 and 0.008 all the way to 0.01. So as you can see, we can cover a lot of frequencies in a very small space. The distance in the horizontal axis between one frequency and 10 times that frequency is called a decade. So according to all this, we have to put in the top graph the values of the third column of the table. These values, the gain, the magnitude of the complex number, these values go here at each corresponding frequency. And in the bottom diagram, we have to put the values of the fourth column, each one again at its associated frequency. Then, joining the points, we get the body plot of the system. That is the two curves defining the frequency response. Well, actually, in the top curve, we don't usually represent plainly the gain, but 20 times the common logarithm, that is the logarithm with base 10 of the gain. And then we say that the gain is expressed in decibels. Why we use decibels will become clear in the next video. Okay, finally, before I leave you, I want to comment that there is a third option to represent graphically the frequency response, an option that combines features of the previous two. It's called the phase versus logarithmic magnitude, or simply the Nichols plot, after Nathaniel B. Nichols. In this plot, we simply take pairs of values depicted in the body diagram and put them in a Cartesian coordinate system. The x-axis is for the phase shift, and the y-axis is for the gain expressed in decibels, 20 times the common logarithm of g. So each point, each pair of points like this has a corresponding point here, and taking some other points, some other pairs of points, and joining them, we get the Nichols plot of the system. Well, as you see, the Nichols plot have the same problem as the Nyquist plot in terms of the frequencies, because we have to identify them with a label next to each point. But at least here the graphs can be added up. And it has some other advantages. It's used a lot for controller design, especially in the field of robust control. But anyway, let's move now to how to draw the body plot of a system.